The lecture title is Hydrogen-Induced Damage in Structural Steels. In this lecture, I'd like to concentrate on some metal degradation mechanisms and the challenges related to hydrogen-induced damage in structural steels. Here there is a presentation outlined. And at the beginning, I'll give you some background about the problem. And after that, I'll consider assessment of hydrogen-assisted cracking using fracture mechanics methods, influence of hydrogen on mechanical properties of steels under operation, susceptibility of operated steels to hydrogen embrittlement and hydrogen-induced cracking, assessment of hydrogen-assisted steels under long-term operation, in laboratory methods of accelerated hydrogen-assisted degradation of steels, and finally, pipeline durability and integrity issues at hydrogen transport via natural gas network. The research questions of the lectures are focused on understanding what hydrogen do when it's going into material, and how hydrogen-induced damage in steel, and why hydrogen influence on worsening the properties so much. Hydrogen penetrates structure of steel, and it has been high responsible for many catastrophes. We know hydrogen goes into material and causes the failures, how it does it, and how it induces damages and affects the properties of steel so much are still the questions that open in the science. And it's really difficult to measure individual atoms of hydrogen-induced steel because it's very light, very small, moves a lot, and hydrogen is highly abundant in the universe. Direct observation of hydrogen in material is very challenging. Hydrogen in metals attracts interest from scientists since many decades. And most of the interesting properties are related to the small size of hydrogen. Its interstitial diffusion accompanied by quantum mechanics and extraordinary high mobility of hydrogen atoms in materials. Thus, for metals, hydrogen diffusivity may reach values as known for ions in aqueous solutions. And thermodynamic equilibrium is reached within a comparably short times, even at room temperatures. Hydrogen damage is a degradation mechanism active many industries, especially in the oil and gas and chemical industries. Here is presented a scheme with a classification of hydrogen-induced damage. And hydrogen metal interactions can occur at high or low temperature, depending below 200 degrees Celsius. Therefore, hydrogen damage takes place at two different regions: elevated temperatures and temperatures at ambient and slightly above. And this lecture will mainly consider low temperature hydrogen-induced damage. Once entered the metal, atomic hydrogen interacts with the metal structure and may produce a damage of various forms, and such as hydrogen embrittlement, hydrogen-induced cracking, blistering, delayed fracture, and others. There are also other damage mechanisms induced by hydrogen in metals when hydrogen is metals or with carbon to form hydrides or methane, respectively. And typical hydride forming metals are titanium and zirconium. In this case, hydride causes the brittle fracture of the metal along the hydride matrix interface. And on carbon steels, hydrogen reacts at high temperature, higher than 200 degrees Celsius, with carbon to give methane. And this phenomenon occurs mainly at the surface of carbon steels, causing decarbonization. And if it occurs internally, methane is trapped like hydrogen in hydrogen-induced cracking, and then creating internal cracks, reducing fracture toughness, fatigue, and creep resistance. This type of damage is often called a hydrogen attack. And there are many classifications of hydrogen deterioration can be found, and the most general ones can divide embrittlement into two groups, internal and external. And the first one relates to the embrittlement caused by hydrogen contained in the metal matrix as a result of manufacturing process. And the second one is caused by exposure to hydrogen, which inserts inside the metal and modifies the mechanical properties. Hydrogen can be available in the metal from various sources, including the electrochemical reduction of hydrogen, water, carbon dioxide, and hydrogen sulfide, and other also ions. And here you can see simplified electrochemical reactions for this hydrogen evolution. Actually, the first stage, the formed hydrogen atom is absorbed, and it either combines to form hydrogen gas or becomes absorbed into the steel. Here there is also presented the most common types of hydrogen sulfide corrosion related to hydrogen damage. Hydrogen often present during corrosion, but may also occur during cleaning procedures and cathodic protection. Hydrogen can also be entered the lattice during heat treatment, welding, and various purification processes. And another ready source of hydrogen is steam, as either a byproduct of welding or as is in a service environment such as piping. Hydrogen also can be evolved due to dissociation of molecular hydrogen, especially on fresh surface caused by, for example, mechanical loading. Hydrogen can be transported at various types of lattice defects in steels. And here you can see a nice illustration by Koyama and others showing different hydrogen trapping sites in steels, such as vacancies, certain solutes, grain boundaries, and phase interfaces, triple points, precipitates, and others. And the main challenge is identifying the governing mechanism behind hydrogen embrittlement lies in mapping hydrogen trapping and kinetics with microstructural sensitivity. Microstructure specific hydrogen mapping is the most important challenge on the way to a better understanding of the underlying hydrogen Pressure of hydrogen is challenging to map due to its low mass, huge embrittling effect already at low concentrations, and a high diffusivity in presence of compositional, thermal, and mechanical gradients. For instance, the average concentration of hydrogen in steels is within the range from zero point 0.1 to 100 ppm. Moreover, hydrogen is diffusible even at room temperatures, and this effect further enhanced in the presence of stress localization. There are four requirements for failure due to hydrogen embrittlement, including microstructure feature, chemical properties, exposure to an environment that contains hydrogen or it's hydrogenating, the presence of tensile stress on the component, and temperature range that supports hydrogen transport in steel. It's between from -50 to 150 degrees Celsius. And it's worth noted that while cracking mechanisms are similar, the rate controlling processes are very different. And a combination of the main mechanism that occurs under hydrogen embrittlement occurs in these are hydrogen enhanced decohesion and adsorption induced dislocation emission. Noted that high strength steels with tensile stress greater than 1000 megapascal are the alloys most susceptible to hydrogen embrittlement. And for a certain hydrogen content in general, steels appear more susceptible as strength resistance increases and the tendency to embrittlement increases, strain increases. Hydrogen embrittlement decreases as temperature increases. And this behavior prevails at room temperatures and disappears above 200 degrees Celsius as dissolved hydrogen escapes out of steel. So a hydrogen-enhanced localized plasticity mechanism is based on sense of solid hydrogen ahead of cracks, specifically in hydrogen atmospheres around both mobile dislocations and obstacles to dislocation movements. By this mechanism, the hydrogen atmosphere is stored when mobile dislocations reach obstacles. That is, the repulsion by obstacles is decreased. And since hydrogen accumulation is localized near crack tips, deformation is localized and facilitates in near crack tips, resulting in raw fracture. And a hydrogen-enhanced decohesion mechanism is based on the weakening of iron-iron intermetallic bonds at or near crack tips due to a decrease in the electronic charge density due to the presence of hydrogen in crystal lattice in interstitial sites. That then favors an easy tensile separation of the atoms. And a fracture surface should appear basically featureless with a less cleavage steps and tear ridges separating decohesion regions. And adsorption-induced dislocation emission mechanism is based on hydrogen-induced weakening of intermetallic bonds crack growth occurring by a localized slip. And it's assumed that absorbed hydrogen weakens substrate interatomic bonds and thereby facilitates the emission of dislocations from crack tips. There is also substantial dislocation emission ahead of the crack tip, which results in the formation of voids around particles or at slip band intersections. And such behavior means that crack propagation occurs due to dislocation emission from crack tips, also with a contribution from the void formation ahead of the crack tip. So here you can see how hydrogen is involved in damaging of pipeline seals of oil and gas pipelines under metal of from the internal and external surface of the pipe due to electrochemical corrosion leads to molecular hydrogen accumulation in certain trapping sites. And such circumstances promote the formation, evolution, and accumulation of micro defects in pipeline steel, or so-called damage accumulation. And consequently, this leads to deterioration of mechanical properties, especially of plasticity and brittle fracture resistance. And therefore, corrosion in oil and gas pipelines is a key issue in safe operations because it accelerates in bulk material degradation due to a destructive role of hydrogen and still hydrogenation, together with working stresses, facilitates a development of in bulk damaging nano and micro scales. And here you can see some examples of revealing of such damaging under mechanical loading. Micro damaging of steels can be often observed by fracture surface analysis. And on this slide, you can see two peculiarities on the fracture surface after tensile tests of smooth steel. On the left, decohesion of inclusions from a matrix. It's one of the reasons of operational damage formation. And on the right, transgranular cleavage as a result of hydrogen accumulation. And here you can see also intergranular cracking and microdelaminations. For rolled steels, delamination is a typical feature for a degraded metal. Hydrogen facilitates decohesion, so it intensifies microdamaging. It is interested in the mechanism of fracture and energy consumption of fracture in areas between these decohesion elements. If a fracture is ductile with more energy consumption, then fracture realizes due to a micro-void coalescence, and a role of hydrogen can consist in formation of high pressure in voids. However, if the area of decohesion these decohesion elements can also be fractured in brittle fracture, usually by cleavage. Assessment of hydrogen-assisted cracking using fracture mechanics methods. Generally, two types of mechanical loading are used, static and cyclic. And for first one, the crack growth rate is as dependence on stress intensity factor and a threshold stress intensity factor characterize fracture resistance. And in the second one, a corresponding dependence of fatigue regrowth rate on delta K and fatigue threshold delta KTH. And is a constant level of crack growth rate in in a wide range of stress intensity factor range. And regarding fatigue regrowth rate, corrosive and hydrogenating environments influence um, on curves changing the typical for tests in error in diagrams. And they can decrease or increase a fatigue threshold, considering middle part of a diagram not influence or accelerate fatigue regrowth. If the middle part of the curve is similar to a plateau, it means realization of stress corrosion cracking mechanism in condition of fatigue. Stress corrosion fatigue, and different frequency causes different plateau curves. Corrosion and hydrogenating environments can change mechanical situation, which usually is not detected by nominal stress intensity factor. A value calculated on base of specimen geometry, a scheme, and a level of loading and crack length. And in this case, possible crack branching, micro, macro, intergradual, etc., and blunting are not taken into account. But they can have some for starting cyclic loading. Another a factor should be taken also into account is crack closure effect, which concerns fatigue regrowth only and consists in prevention of crack closure during part of unloading. The real stress intensity factor range is less of nominally calculating. Just effective stress intensity factor range is real mechanical driving force of a fatigue crack growth. Influence of hydrogen on mechanical properties of steels under operation. There are many types of mechanical damage and failure associated with the presence of hydrogen in metal. Hydrogen steel may to increase in ductility, embrittlement, blistering, and cracking that occurs at lower loads than measured in the absence of hydrogen. And hydrogen accumulates in areas of high stress and may reach a critical concentration, potentially causing fractures and catastrophic damage. Hydrogen atom readily diffuse in metal lattice and pose serious threat in mechanical strength and ductility. Influence of hydrogen on mechanical properties of steels under operation can be evidenced by a mechanical testing of material samples extracted from the operated structure. And here presented scheme demonstrates degradation of low carbon and low alloyed pipeline steels. The first stage is the deformation aging, and the second one is a damage accumulation. This damage accumulation or so-called dissipated damaging. It's well known that under strain aging, the strain and the hardness increase, and um, plasticity and resistance to brittle fracture, for example, impact toughness and stress toughness decreases. However, this tendency of mechanical properties changes could be violated if the metal undergoes bulk damage accumulation during operation as a result of hydrogenation. And it's known that hydrogen promotes the formation and and production of defects gives also the embrittlement. So hydrogenation intensifies the damaging process due to hydrogen-induced microcracking and of steel, and in this way facilitates its mechanical degradation. And in such circumstances, stress, strength, and hardness decrease, and elongation increases. And a further operation of the degraded steel leads to additional decrease in reduction in area and characteristics of brittle fracture resistance. Such a mechanical behavior of a metal doesn't typical, and because a decrease in strength and hardness is accompanied by elongation is accompanied by simultaneous decrease in reduction in area. Here presented mechanical properties of pipeline steels in as received state and after operation. And as we can see, the main peculiarity of operational hydrogen-assisted degradation of steels consists in a decrease of plasticity and brittle fracture resistance. Regarding the characteristics of plasticity, special attention should be paid for assessing elongation. The issue is in the following. Operation due to a long-term mutual effect of hydrogen and working stresses causing development of microdamaging in steel, and tension, and then elongation will summarize really plastic deformation and multi-cracks opening, and it will at least diminish elongation or even increase. On the slide, you can see that operated for 30 years steel is characterized by the least value of fracture toughness, but the highest value of elongation. And hardness of the damaged steel is also lower than that for as received steel. And intensification um, the damage in steels can be evidenced by behavior in steels by hydrogen extraction and permeation methods provide valuable information for assessment of degree of in-service dissipated damaging. The hydrogen permeation method of Devansan-Sakursky is used, taking into account that the hydrogen in a metal is located mainly in defects, which considered as hydrogen traps. And thus, using this method, can lattice and apparent hydrogen diffusion coefficients can be determined, and the ratio is a measure of the trapping efficiency. And here you can see that the operated steel is distinguished by higher resistance. It means a high level of micro damaging. And using hydrogen extraction method, it was obtained that in the case of steels in the initial state, most hydrogen was dissolved at a low extraction temperature, 200 degrees Celsius, whereas the operated steel is characterized by higher temperature of desorption, indicating hydrogen trapping by sites with higher energy. And it's important to emphasize that it's not really the hydrogen concentration causes embrittlement, but rather hydrogen diffusivity through the steel. And as you can see on this slide, a decrease in brittle fracture resistance is in a good agreement with hydrogen concentration in metal. Higher hydrogen concentration is corresponds to a lower level of impact toughness. Here the result show effect of long-term operation under atmospheric corrosion on mechanical properties of carbon steels. Generally, they are characterized by higher impact toughness values. However, for the lighthouse steel operated for more than 100 years, we have a combination of a very low impact strength for arc iron. Such low hardness can be a result of very intensive damaging. There is no other explanation for this. And correspondingly, this intensive damaging leads to a very low brittle fracture resistance, namely, in this case, impact toughness. And such a situation is similar to gray cast iron, which also is characterized by um, a combination of low hardness and strength and extremely low brittle fracture resistance. And so it was assumed that this damaging is a result of a long-term effect of hydrogenation of steel due to atmospheric corrosion. As it was demonstrated in numerous studies, condensed on steel is hydrogenating due to acidifying under wet-dry cycle. Here you can see results on effect of a wet-dry cycle on hydrogen permeation obtained by Omura with others. Here you can see another example of hydrogen-assisted degradation of carbon steel under operation and dependence of steel degradation degree on the sign of operational cyclic loading. The material under study was low carbon steel obtained from a stacker conveyor boom after 30 years of service. This boom frame of a stacker conveyor was subjected to atmospheric corrosion and operation. And as it was shown, that atmospheric corrosion is accompanied by hydrogen erosion. So here presented data show relative changes in mechanical properties of the carbon steel in different state. Um, a minor change in strength characteristics of operated steel compared with the reference steel was observed. A reduction in area and elongation at fracture were decreased as a result of a long-term operation. And as can be seen from these results, both tensile and compressive cyclic loading and the operation leads to plasticity deterioration. Here is the result of degradation of brittle fracture resistance of the steel. Thus, at ambient temperature, the impact toughness values of the operated steels were in about 30% lower than of the reference steel. And the extremely low values of impact toughness were obtained at testing at temperature of minus 40 and 20 degrees Celsius for all operated steels. So as you can see, decrease in impact strength of steel due to long-term operation was almost the same for both studied operated steels, irrespective of the sign operating steel. On this slide, results on fatigue growth propagation in the operated under tensile loading steel and in the as received and in the reference steel in air and in a corrosive environment at different stress ratio. It should be noted that a high plasticity of the study steel and thin thickness of the specimens limited by angle bar thickness and high stress ratio significantly limited stress intensity factor range for which it was possible to obtain fatigue growth values and build the kinetic diagrams. So as it can be seen from this data, these values of stress intensity of minimum thickness of specimens to ensure plane strain state are in the near threshold region of the fatigue growth curves. Therefore, only the threshold stress intensity factor range can be considered as characteristics of the steel. And the difference in fatigue growth rate revealed for different stress ratio are associated mainly with a decreasing effect of fatigue crack closure effect at increasing stress ratio. And at the lowest stress ratio, 0.1, in surface degradation of steel had no notable effect on fatigue growth in air. I mean, fatigue growth rate anymore. Difference in fatigue growth rate values for the steel in different states was revealed mainly in the stress intensity in the near threshold region of stress intensity factor range. And at higher values of stress intensity factor range, the difference was not observed. And the environmental effect on crack growth rate investigated for the post-operated steel and reference steel was different. Thus, for the reference steel, the corrosion environment retarded fatigue growth, especially in the near threshold region at stress ratio 0.6. However, for the operated steel, the environmental acceleration effect on crack rate was revealed at a higher stress ratio 0.75. And the rapid increase in crack growth rate observed at this higher stress ratio was associated with susceptibility of stress corrosion fatigue. And so hydrogen-assisted degradation of the carbon steel operated under tensile and compressive cyclic loading was manifested in degradation of plasticity and impact toughness, and also a fatigue growth rate in the post-operated steel was accelerated in a corrosive environment, especially diagram indicated its susceptibility to stress corrosion fatigue. Here you can see another example showing deterioration of resistance to corrosion fatigue regrowth under operation. And cathodic polarization of steel in corrosive environment causing its hydrogen charging leads to an increase in fatigue regrowth rate more intensively for operated damaged steel in the medium amplitude region of loading, the Paris region, often with a plateau of rate on the curve. This is due to a combination of mechanisms of fatigue and stress corrosion cracking. It means that realized and fatigue growth is significantly induced by sustained load. And here is demonstrated effect of internal hydrogen on fatigue growth in the operated pipeline steel. When a hydrogen diffuse to a prefracture zone through in bulk metal. Fatigue growth in steels is usually studied under conditions of filling crack cavity to by hydrogenated environment. However, in this case, to study effect of internal hydrogen, a special scheme of fatigue testing and hydrogen electrochemical charging has been developed. As you can see, only lower, just a second, only lower part of the specimen was subjected to electrolytical hydrogenation, and at the same time, upper part of the specimen was with a growing fatigue growth. Fatigue crack was in air, and hydrogen absorbed by a metal due to electrolytical hydrogenation um, moves by diffusion to crack tip and effects on crack growth rate. And this figure demonstrates such effect. We can see acceleration of fatigue growth in the operated pipeline still by internal hydrogen. The next is susceptibility of operated steels to hydrogen embrittlement and hydrogen-induced cracking. Generally, operated steels are more sensitive to hydrogen embrittlement. And on the right scheme, you can see a little difference between plasticity of different state of steels, but the left one demonstrates a significant difference if to compare results of tension tests of hydrogenated specimens. Susceptibility of steels to hydrogen embrittlement can be studied by tension of specimens in air after their hydrogen precharging electrolytically. And the plasticity characteristics of steels without and after hydrogenation from the point of view of compared and susceptibility of steels to hydrogen embrittlement can be evaluated by the change in plasticity characteristics. And also here you can see research results demonstrated that both studied steels of casing pipes were sensitive to hydrogen embrittlement. And here presented data on investigation of different zones of weld joint of pipeline steel in as received state and after about 30 years of operation. And the specimens were tested by tension in an S4 test solution simulating a soil environment and potential of cathodic protection. And as it can be seen from these results, the operated weld joint is characterized by higher sensitivity to hydrogen-induced cracking. And especially the weld metal of the operated weld joint is the most sensitive to hydrogen-induced cracking amongst the different zones of operated weld joint. And in order to assess susceptibility to hydrogen-induced cracking, electrochemical method of hydrogen permeation can be also used. And for this purpose, electrochemical permeation cell Okay, a cathode and anode can be is used, and a specimen steel membrane is located between the chambers. And in the cathode chamber, cathodic current is applied to the hydrogen input side of the metal membrane, and it's periodically increased step by step. And on the hydrogen output side, hydrogen permeated through the membrane is oxidized. And increasing cathodic current each time leads to the increment of anodic current density in the oxidizing cell. And this layer of membrane becomes damaged due to combined action of hydrogen and residual stresses induced by intensive hydrogen charging. And in such a case, a sharp decline appears on the oxidizing curve of the hydrogen output side of the membrane. And this indicates the trapping of hydrogen with newly formed defects. That is the development of hydrogen-induced damaging. And thus, the cathodic current density, which corresponds to defect occurrence, is considered as the critical. And it shows determining the mechanical susceptibility to hydrogen-induced cracking. And as it can be seen from initial state in comparison with the operated steel is characterized by higher level of the critical cathodic current. It means it more resistance to hydrogen-induced cracking. Rolled steels are commonly susceptible to delamination cracking, since they are characterized by a bending microstructure, and non-metallic inclusions are also elongating in the rolling direction. Here you can see typical microstructures of rolled pipeline steels. And generally, the lamination is formed by a plane with relatively weaker texture parallel to the rolling plane within the steel due to any aspect that leads to anisotropic microstructure, including plastic deformation and so on. Damaging also accumulates in the rolling direction during long transition, facilitating cracking along the pipe axis. And a hydrogen charging of a metal from inside of the pipe due to electrochemical corrosion leads to molecular hydrogen accumulation in certain trapping sites, for instance in the intergranular defects, inclusion matrix, and the creation of high pressure in them. And hydrogen being accumulated inside the delamination cavity eventually leads to a pipeline damage. And as a result of excessive hydrogen pressure, fracture often takes place even in the absence of any external loading. A common feature of delamination cracking in pipelines is that fracture propagates in a circumferential direction, which often results in a pipeline fracture. And here you can see that extensive delamination of the pipe wall in two natural gas pipe elbows operated for 40 years, varies a pipe wall swimming under ultrasonic testing. And such a delamination covers a large area on attention part of pipe elbows. And in one of them, there was also a crack revealed. Formation of as a result of a pressure of recombined hydrogen being accumulated in the delamination. And it was confirmed by the fact that the crack growing from the macro defect opened on the outside of the pipe at some distance from the lamination counter. And here you can see results of laboratory testing of mechanical properties of this steel, and the testing was performed using standard smooth cylindrical specimens and also notched specimens in order to estimate mechanical axis. And so and cross transversal specimens were tested. And the pipe elbow still was characterized by lower plasticity in comparison with the straight pipe run, regardless the right elbow section was tension or stressed. Moreover, the highest decrease in reduction in area values was inherent to the steel of the tensioned pipe elbow section compared to the straight pipe one. And it should be noted that to determine the plasticity characteristics of the pipeline steel with damaging susceptible to hydrogen-induced cracking, correctly notched specimens duration concentration in the cross-section location only. Here, presented data show susceptibility of the steel of straight and tensioned pipe sections to hydrogen embrittlement. And it's obvious that the steel of the tensioned pipe section was characterized by higher sensitivity to hydrogen embrittlement, especially under testing short transversal specimens, in which a fracture plane is parallel to the action. It means the most damaged plane. Here you can see also fracture surfaces of specimens of tension section delamination. And the feature of specimen due to its origination, microdelamination from non-metallic inclusions and brittle transgranular cleavage. The steel of tensioned pipe section, being the most degraded during operation, was characterized by the lower values of fracture toughness, and also very low values of impact toughness of steels were obtained under testing short transversal specimen. So it should be also noted that when longitudinal specimens were tested, a number of delaminations on fracture surface were observed. Here you can see on my so another case of the extensive delamination of pipe steel was detected on two sections of the above ground natural gas transit pipeline crossing a river. So two cases were revealed. The first one, only the upper part of the above ground characterized by delamination, almost from one welt butt weld to another one. Another example of a full delamination between two butt welds was observed. And of this is that high pressure hydrogen are located between these pipes and fracture. And there is a common feature for all considered that pipes were up above ground. It means that they were subjected to climatic temperature changes, and therefore there were conditions for moisture condensation on the pipe internal surface. And as with earlier, condensed water serves as a source of hydrogenation due to corrosion, and thus hydrogenation of pipe steel from internal surface is possible. And hydrogen diffusing from the internal surface in the direction to external surface can be trapped in different defects and recombine into molecular state. Of course, such problem, the problem of extensive delamination, is associated with preliminary uh, mm, metal degradation during long-term service. So more operational degraded pipe steel due to microdelaminations is more sensitive to hydrogen-assisted macrodelamination. And the phenomenon of macrodelamination is clarity for above-ground pipelines transported natural gas, and it can be assumed that the main reason for its formation is pipe steel hydrogenation as a result of internal electrochemical corrosion. So, a mechanism of hydrogen embrittlement of steels under long-term operation. The embrittlement of pipe is a well-known phenomenon, but the precise role of hydrogen in this process is not well understood. And here a new model is proposed wherein hydrogen facilitates a carbon diffusion in ferrite perlite pipeline steels under operation, which leads to carbides enrichment, both grain boundaries and intragranular defects, and thus promoting a cleavage fracture. So the background is as follows. Changes in microstructure of long-operated pipeline steels of gas transit pipelines observed experimentally as precipitation of carbides at the grain boundaries, as it was reported by Chivildeev, and presence of carbides at grain boundaries stress corrosion cracking resistance of pipeline steels under operation. And it was suggested by Nechayev that during a long-term operation of steels, carbohydrate-like and other nanosegregated structures are formed at grain boundaries. And according to his calculations, for formation of the carbide at grain boundaries, it's enough diffusion of carbon from the grain body to the boundaries at a distance of 1 micron only. During, of course, a long term, 10, 20 years of operation of gas pipelines. And this phenomenon is associated with maintenance pipeline steels under operation. And it was assumed that diffusion of carbon not only to grain boundaries but also to various defects inside grains, boundaries of subgrains or other defects took place during long-term operation, and it led to formation of nanoparticles of carbides at these sites also. And under service conditions, diffusion of carbon can be significantly intensified by hydrogen being absorbed by steel. It's well known that hydrogen intensifies diffusion of other elements in steel, including carbon. And precipitations of carbide nanoparticles causes steel embrittlement and consequently leads to brittle fracture and reduction in fracture energy. And in such circumstances, both intergranular cracking of pipe steel under surface and a transgranular cracking of post-operated steels under impact toughness testing are associated with this phenomenon. And under such a mechanism of in-service degradation of metal, fracture surface should be enriched by carbon compounds, a carbide type, and as it's known, electrochemical characteristics should be sensitive to this enrichment. Here we can see a dependence between electrode potential of content in steel. It's confirmed a known general trend of a negative shifting of potential with increase in carbon content in carbon steel. And here also presented results of electrochemical experiments performed on the fracture surface of specimens from X52 pipeline still in different states being fractured after impact toughness testing with brittle fracture and on the polished surface. The significant difference between potentials measured on polished and fracture surface for post-operated steels was revealed. These steels were operated during for about 30 years and decreasing. According to the presented data, the steel with the highest degradation degree was characterized by the most negative shift of potential compared with the as-received state. And such a significant difference in the potentials can be explained by the fact that the fracture surface is the result of propagation of local sites characterized by minimal resistance of material in fracture. Therefore, changes in the metal that were initiated during the long-term operation and caused its mechanical properties degradation are the most distinguishable on the specimen fracture surface. And the obtained dependence, this difference in potentials was explained by the increase in carbon content due to precipitation of carbides directly on the fracture surface. That is, a fracture surface was enriched by carbon compounds. And this fact can serve as a proof of assumption that a long-term operation of pipeline steel caused its embrittlement due to precipitation of carbide nanoparticles not only at grain boundaries but also at intergranular defects. And hydrogen absorbed by steel under operation significantly influence on this process. And it should be also noted that under such embrittlement, a decrease in brittle fracture resistance of metal caused by long-term operation should be expected for both intergranular and transgranular fracture mode. In laboratory methods of accelerated hydrogen-assisted degradation of steels. And development of accelerated methods for in laboratory hydrogen assisted degradation of steels is very important since they allow predicting the changes in mechanical and other properties of structural components during their service, or at least comparing different materials regarding the stability of their properties during service. And such methods are applicable not only for hydrogen assisted degradation of steels, will be useful also for operated materials since will be able to assess their susceptibility to degradation under further service. And the question is how to simulate changes in material in laboratory conditions similar to real degradation. And from this lecture, you have already known that operational in bulk material damaging is the most dangerous for structural integrity. So we will try to simulate a development of damaging in laboratory conditions. Here it should be mentioned the existing method of in laboratory deformation aging of structural cells, which consists in axial loading up to strain value of 10% and artificial Celsius for 1 hour. And such a procedure provides a deformation aging due to formation of collateral clouds which block mobility of dislocations. And this corresponds to the first stage of material degradation when strength increases and whereas plasticity and brittle fracture resistance decreases. And in order to reach the second stage of in-service degradation, we have to modify the method by including the step which causes intensive in bulk damaging. And this can be achieved by preliminary hydrogenation of specimens. And only after that, loading to the certain a value and then to artificial aging. And is a simultaneous action of hydrogen absorbed by metal and deformation will cause micro damaging in a metal. And here you can see a comparison of change in plasticity characteristics of steel after its treatment using these degradation methods. In the middle is the operated pipeline steel, and on the left the result of the known method of deformation aging with two levels of plastic deformation, 5 and 10%, and on the right using the developed method. So it's obvious that the conformity to the real steel state after operation. Also, is on relative changes in impact strengths in steel after its treatment using these methods, and material degraded in laboratory conditions is characterized by a similar extra as the steel after a long-term operation. Low pipeline integrity issues at hydrogen transport via natural gas network. Hydrogen will play a significant role in a decarbonized energy system in the coming decades, and it can be long distances by pipelines. Accordingly, it's advisable to consider the possibility of transported hydrogen only by pipelines specially built for this purpose, but also use the existing network of gas pipelines. At the same time, the problem of violation of steel pipe integrity due to the well-known negative impact of hydrogen on the mechanical properties of steels should be considered. One of the most important issues is hydrogen embrittlement, as well as decrease of resistance to brittle fracture, and because it's often responsible for unpredictable low energy fracture of metal component. So Ukraine has the experience transit pipelines, and they have not been used currently to full capacity due to a significant reduction in gas transit. And the future process of decarbonization will only force this situation. And according to the European hydrogen backbone vision, one of the steps of extension of hydrogen transport infrastructure can be a repurposing of existing gas infrastructure. And Ukrainian gas pipelines can be served as a transit route for hydrogen from Ukraine and Southeast Europe to other European Union countries. Ukraine has joined European Hydrogen Backbone Plan, initiative to have an operating network of hydrogen pipelines in Europe by 2040. However, long-term service of gas pipelines causes still degradation, and evidently hydrogen plays in this important structure. So possible hydrogenation of pipe steel due to hydrogen transportation can cause or intensify hydrogen embrittlement and hydrogen-induced cracking. So on this slide, you can see example of stress corrosion cracking of pipe from its internal surface. However, if pipe will hydrogenate from internal surface and hydrogen in it will move to opposite wall side, this hydrogen can also embrittlement, so it will be hydrogen cracking and not stress corrosion cracking. Such situation can be modeled experimentally by holding of specimen with cracked electrolytes. I was a third area. And consider it a possibility of pipe wall hydrogenation from a pipe internal surface. It should be taken into consideration at least two mechanisms of hydrogenation. The first one consists in electrochemical interaction of metal surface with condensed moisture with evolution of hydrogen. This medium inside of the pipe contains at least bicarbonate ions, which and therefore a transported natural gas due to a certain degree of its humidity can also be considered as aggressive not only because of corrosion of inner surface of pipe but also hydrogenation of pipe steel. And it should be also noted that only part of atoms generated by corrosion can be absorbed by a metal. Therefore, most of them in molecular form remains in transported environments. And gaseous hydrogen is another source of hydrogenation. Molecular hydrogen should fastly dissociate to atomic state, and only then it can be absorbed by a metal. And dissociation energy on a metal without any corrosion products or are the films. And the inner surface of pipeline is covered by such films, but they can be breached by applied stresses, especially cyclic loading, exposing the freshly formed metal surface. And thus conditions for the dissociation of molecular hydrogen can be created. And cyclic overloading of pipes is especially dangerous in this case. Atomic hydrogen absorbed by a metal, regardless of a source of hydrogenation due to high diffuses into a pipe valve towards an external surface. And this process is facilitated by stress gradient through pipe And atomic hydrogen facilitates brittle fracture of steels. Moreover, it can recombine to molecular state in microdefects, and as a result, high pressure hydrogen inside traps results in an increase in inner stress generated in steel in the vicinity of defects, which could reach values commensurate with stress induced by a gas pressure in pipe. Hence, combinations of high stress generated by molecular hydrogen in defects and lower resistance to brittle fracture of material hydrogenated by atomic hydrogen lead to development of damaging by mechanism of hydrogen-induced correction to a diminished state of hydrogen in the pipe steel. We have developed the special methodology of study of possible effect of interaction on pipeline steel properties due to hydrogen transportation by gas pipelines. The main peculiarity consists in a long-term holding of a specimen in a pipe with hydrogen or hydrogen natural gas mixture, and preloaded specimens will be exposed to hydrogen from 3 months to 3 years in the field with the following in laboratory testing. For prevention of hydrogen desorption at transporting specimens from the field to a laboratory, they will be held in a liquid state. You can see the assembled stand with two pipes enabling samples in hydrogen or a natural gas hydrogen mixture at a certain pressure under conditions similar to those inherent to above ground part of natural gas pipelines. They are subject to climatic temperature changes. And the main task of such a study is revealing of specimens hydrogenation and also its effect on the mechanical characteristics, especially brittle fracture resistance and hydrogen embrittlement. The main methodologies of experimental studies of influence of hydrogen or hydrogen natural gas mixture on pipe steel durability, of mechanical behavior of as received and overlaid steels. Since witness flat samples in pipes with hydrogen could be hydrogenated from surface, samples of reduced thickness should be preferred, and in our case is 1.2 millimeters. And secondly, flat tensile specimens cut out of pipes in the transversal direction, since they will provide fracture in direction of rolling plate, which is used for pipe manufacturing. And it's to our experience, such specimens are more sensitive to in-service degradation in comparison with long-term holding. And that's bring me to the end of the presentation, and thanks so much for your attention and listening.